as of now. Okay, so good morning, everybody, and welcome back to Math 115. So today is the second day. We're going to do some more review, basically. Actually, pretty much the first 2 weeks are going to be entirely, at least theoretically, should be review. And because of that, the first 2 weeks of 115 are always really awkward, at least for me, because I feel like in order to do the review, you have to cover like a lot of different topics really, really quickly, which leaves not as much time as I would like for like activities to keep you all engaged with like active learning. So I'm going to try to pepper some in here and there. We're going to try a little bit of partner work today just because I feel like it would be a little weird to try to do like groups when you're organized in tables like you are right now. So we're going to try partners today. But 2 quick announcements before we start regarding the homework. So there are 3 homeworks that currently have a due date. There are more homeworks in the system, which I'm going to kind of just adjust the due date as we go along. So right now, all of the homeworks are set to be due at like the end of the semester. I'm just going to move back the due date for the requisite homework assignment as necessary. So the first 2 are A.1 Part A and B. Those are going to be due on this Thursday. It's kind of a lot of questions, actually, in A.1 and A.2. But I think you'll find that if you were able to pass the math placement test or you have otherwise qualified for this course, I think that you should find most of them take you like 10 or 15 seconds to do. So high volume, but I think that most of the problems are pretty simple and shouldn't take you very long to do. Then A.2 is what we're going to cover. We're probably going to cover A.2 tomorrow. And then that homework will be due on Friday, and that has some polynomial problems in it. And just generally, I think that the homework assignments which have been given to me, I think are a little bit long. So I've been trying to pare them down. But just keep me posted in the anonymous survey if you feel like you're drowning from homework. But that's not my intent. I just want to give you enough to help you practice to learn. Any questions about homework? Okay. Well, if you have questions over like specific questions over the math part of the homework, please come to office hours. So that's today from 10 to 11:30. And also Wednesday from 10 to 11:30. Yes?
Is Part B posted yet?
It should be, yes.
I just see Part A.
It might be because Part B. If not, then we'll recap what we did last time really quickly, and then we'll get into some new material. So last time we talked about basically just 2 things, which was PEMDAS and, I count PEMDAS and fractions in the same thing. And then the only other thing we talked about besides basic arithmetic was preliminary set theory. So let's recall that the definition of a set is just a collection of items, okay? They could be, for our purposes, 100% of the time, they will be numbers. But you could also have a set of like functions or something like that. So you say I have a bucket, and into my bucket I put the function x squared and x cubed and that sort of thing. But mainly just think about a collection of numbers, okay? So you could take, for example, the set 3, 7, and 9. Okay, so that is a set containing the numbers 3, 7, and 9. And we call 3 an element of the set A because it is contained in that set. Okay, so think of like a bucket, and depending on whether or not something is in my bucket, I say it's either an element of the bucket or it is not an element of the bucket or set. Okay, then we talked about union and intersection, which is ways in which we can combine sets. So if we combine sets using a union, we just take everything that's in either set or both, and we just make a new set out of all of that stuff. And for intersection, we can loosely think of union as an intersection as meaning or and respectively. So if you do the intersection, then you form a new set which contains only those numbers which are common between both of the first two sets. Okay, so that was intersection, and then we had set difference, and minus is how we subtract elements from a set, and then we had the empty set, which is just a set with nothing in it. End parentheses. Okay. So that was set theory, and then after that we started talking about a handful of examples of sets of numbers, and this is basically where we left off. So we started with the natural numbers, which is a set of numbers which contains all of the numbers which are positive whole numbers, where I'm using whole in the like elementary school version of the word whole. Right? I mean non-fractional, basically, when I say whole here, which is a little bit different from the quote-unquote whole numbers as a set, which refers to all whole numbers which are non-negative. So the difference between natural numbers and whole numbers is that natural numbers have to be positive. Positive means bigger than 0, whereas whole numbers simply have to be not negative, okay, or non-negative, right? So 0 is the only one that is not common between the natural numbers and the whole numbers. So we don't have a fancy notation for the whole numbers like we do for the natural numbers. But what would I get if I did say, let's say that, okay, let's just make up a notation for it. Why don't we do a W with like one of those crazy lines? We'll do something like this. That could be cool. All right, so what would I get if I took the union of the natural numbers and the whole numbers? What would I get if I took the union? Now, union means or, right? Do you want to answer? Oh, I thought you were raising your hand, so you can. No, yeah.
Wouldn't it just be 1, 2, and 3?
Yeah, it's gonna be, well, if we take the union, right, then we take all the numbers which are in either the natural numbers or the whole numbers. So in particular, for 0, do we think it should be included or not included?
Not included.
Not included? Well, if we're doing a union, we want to pick all of the numbers which are in the naturals or in the wholes. So since it is in the wholes, but it's not in the naturals, we're still going to include it because we're doing a union here. Okay, we're going to do a union here. All right, so I am going to keep 0, and I'm also going to keep all the other numbers because, look, 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 blah. All of those numbers are common between both. So since they are in either the naturals or the wholes or both, then we say that they are included in the union. So this is just going to be the set of numbers 0, 1, 2, dot, dot, dot. Okay, so we keep 0 by virtue of the fact that it's in one of them. It only has to be in one of them for a union. All right, what about the intersection? Now, this is the numbers which are in the naturals and in the whole numbers. So in this case, are we going to include 0? No, we're not going to include 0. Can someone explain why I'm not going to include 0?
Because it's the common ones inside both.
Sorry?
The common ones inside both.
Yeah, the common ones inside both include numbers like 1 and 2 and 3 up going on, right? But 0 is in the whole numbers, but not in the natural numbers, which is why it would not be included in the intersection. Is this, how are we feeling about this? Is this like just really abstract, or we're feeling okay about it? I like to do thumbs sometimes. I say, everybody, we're gonna put our thumbs up, and we're gonna do a thumbs up if we feel great about it. We're gonna do a thumbs down if we feel absolutely terrible, and we're gonna go somewhere in between if we feel like we're somewhere in between. So let's try that now. Let's see some thumbs here so that I can get an idea of where everybody's at. Okay, cool. All right, so the next set of numbers we talked about was the integers. So for the integers, the only new things that we're adding is now we're going to say they're whole numbers which could possibly also be negative or 0, right? So we're going to include all the numbers like -1,500,017 and also all of the other whole negative numbers and also all of the whole positive numbers and also 0. Okay, and the notation we use for that one is we draw this funny looking Z where we just do an extra line on the Z in the middle. Okay, so now we've covered the naturals and the wholes and the integers, and now I'm going to consider an even larger class of numbers, which is called the rational numbers. And can anyone tell me what is going to now be included in the rationals that we haven't already included in everything up to now? Fractions, right? So what does the word rational mean? Well, if you take the first part of the word rational, we get ratio, right? So ratio is a ratio of two numbers, something like A divided by B, right, is how we express a ratio or a fraction of numbers. So we're going to include fractions now. So we're still going to include all of the other stuff we've done so far. So ... We're also including -2 and -1. That's fine. But also things like -3/4 or 1/2 or 0.6 repeating or 0 or 1. ... Okay? So we include all of the integers and we just add to this set. So I've got a big bucket, and in my bucket I put all of the integers in the world that there are, which is an infinite number of numbers, right? I put all the integers that there are, and now I'm going to also add into the mix any number that I get by taking an integer and dividing it by a different integer, okay? So if I take -1 and I divide it by -2, I would get +1/2. So I'm going to throw that into the mix too. And all these other numbers, okay, that I can get by doing fractions, okay? All these other numbers that I can get by doing fractions. Okay, so you'll notice that I included something like 0.6 repeating. Now, you might have heard something about irrational numbers. Anybody ever heard of irrational numbers? Can anyone characterize irrational numbers and tell me what it means for a number to be irrational? Yeah, Griffin?
Isn't that when, like, if it's like in the decimals, then it's not, it's like random, or it's kind of like pi or something?
Yeah, so pi is the perfect example of an irrational number. And the difference between an irrational number and something like 0.6 repeating is, yes, it is a decimal. Yes, it goes on and on and on forever. However, if the decimal repeats, then we know that it is going to be a rational number. So if you do like 0.1, 2, 3, 4, 5, 6, 7, and then it's like 8, 8, 8, 8, 8, 8, 8 forever on after that, or if it's like 865, 865, 865 forever on after that, that's what we call a repeating decimal, and we use this little bar up here to refer to a repeating decimal. So we could get 0.6 repeating by taking 2 divided by 3, for example. Okay, so how do we actually tell whether a decimal is repeating or not, or how do we figure out what is the repetition? Well, one thing you can do is just try to do like the following. So if we want to take like 2, and I'm going to bring back some really ancient technology for you all that you might not have seen since, like, I don't know, elementary school, but we use this technology to do division, right? So we put the thing that we're dividing underneath, and then we put the thing that we're dividing by out front, right? So this is called the divisor here. So we're trying to divide 3 into 2, but 3 doesn't go into 2 any times. So we put 0 first, and then comes a decimal, and then we put a decimal here. And now we want to know, okay, this is the 10th place, right? So now we want to know how many times does 3 times 0.1 go into 2.0? And the number of times that 0.3 goes into 2 is 6. If we multiply 6 times 0.3, we get 1.8, okay? And then what do we get? We subtract this, and now we're left with just 0.2, right? Now I want to know how many times does 0.3 go into 0.2? Well, it doesn't, so we have to go one more decimal place over. Now we're in the hundredths place, right? Is this familiar to everyone? Okay. So this is how we do long division, right? We just divide this into here, and you'll notice that after a while you'll be like, oh yeah, every single time it's always something like 1.8 or 0.18 or 0.018, and then we're dividing that into something like 0.2, and you'll get 6, and then keep going and on forever, and you can say at that point that this decimal is repeating. So that's how you figure it out if you want to know. Okay. Any questions about the rationals or about repeating decimals? No? All right. Well, let's throw in basically the rest of them. Okay, so the real numbers. Okay. Oh, I forgot to tell you the symbol for rationals is a Q with a line through it, like so. Okay, so let me remind you also of the inclusion notation. So let's talk about the number -6/7. Is this number rational? What do you think? Yes or no? 6/7? -6/7? Okay, I'm seeing heads nodding yes. I think it is irrational. It's irrational by definition because it is an integer divided by another integer. Okay? So the way that I would write down that -6/7 is a member of the set of rational numbers is I would use my is a member of notation, which looks like a backwards 3 kind of. Looks like this, right? And this means is a member of, or is an element of. And then I would write the symbol for the rational numbers. So when I write this down, I'm referring to the collection of all the infinitely many rational numbers, and I would say, if I take that bucket, this is a statement which says that that number is in that bucket. All right? Fairly straightforward so far. Are we all good? Okay. So let's talk about the reals now. So what do we have to add to the rationals to get the reals? Well, we just talked about it. We need to add in all of the irrational numbers. Okay, we have to add in all of the irrational numbers. And you've probably only really heard of like maybe 2 irrational numbers. I would say probably pi. Anyone know the other irrational number that's pretty famous? It's like 2.714 something. Yeah? It is E. Very good. So throw in pi and E and other non-terminating, that means goes on forever, and non-repeating, that means not repeating. Not repeating decimals. Okay, so numbers like, so we're going to get the set with like all sorts of different stuff, but ... we're going to include -2, -3/4, also negative pi, and E, and 1, and 0, and ... all this other stuff. And the symbol we use for that one you're probably familiar with. It's the big R with an extra line. Okay? It's the big R with the extra line. And so, okay, one interesting fact, or at least I think it's interesting, is that when I was like an undergrad, or when I was in high school, and probably when I was an undergrad until I was like a senior, I used to think that like, well, there's way more rational numbers than there are irrational numbers, because I've only ever heard of like pi and E, for example. But it turns out actually that, yeah, there are way more irrational numbers than there are rational numbers, which is kind of interesting. But if you're interested in that, you can go take a class called Real Analysis, where you can learn a subject called measure theory, and they'll tell you about just how little rational numbers there actually are. Okay, how about complex numbers? Just for fun, we're not going to study complex numbers in this class, but the most famous complex number is I. And what is the deal with I?
Imaginary?
It is imaginary, and what is it set equal to? The square root of -1. Okay, so why is this imaginary? This is imaginary because how can you take two numbers and multiply them together and get -1? If they're the same number, then they're either positive, positive, and you multiply them together, you get a positive, or they're negative and negative, and you multiply them together and get a negative. So how am I going to take a number and I multiply it together with itself and get -1? Well, that's why we call it imaginary. There are actually extremely practical physical uses for complex numbers, including differential equations, which is the mathematical language that we use to describe literally every physical process. So if you're an engineer, I think you should care about them, but we'll leave it at that for now. We're not going to talk much about complex numbers going forward. But you can add complex numbers into the bucket of reals, by the way. All real numbers are also complex numbers, not so in the other direction. So basically, this kind of goes like the naturals are a part of the wholes, which are a part of the integers, which are a part of the rationals, which are a part of the reals, and the largest class of numbers is the complex numbers, which we also throw in imaginary ones. Okay, so that's all of our sets of numbers. Okay, so what I'd like to do now is a little activity. So try to partner up with somebody. If you don't have a partner, that's okay, don't panic. But what we're gonna try to do is classify a handful of numbers using our notation, okay, and of course our fancy letters. And we're gonna try to form a written statement, okay, about the membership of these numbers to various sets. So for example, if I were to do the number -1/2, I know that -1/2 is a rational number, and I also know it's a real number. So I'd like us to write down the sets of numbers to which each of these belong. Okay, so we're going to work on that for maybe 2-3 minutes with a partner, and I'll come around and answer questions as they arise.
I mean, I feel like that would work, honestly. Oh my god.
There is a notation for complex numbers. It looks like this, like a C with a line through it. But yeah, like I said, you don't need to worry about whether they belong to the complex numbers, because every number is a complex number. Come on.
So -1.
Yeah, or if you, just focus on, I would say focus on the smallest class of numbers to which they belong. Smallest as in least amount of members.
So the smallest you can like classify.
Exactly. So for example, 1, what's the smallest class of numbers that 1 belongs to? Sorry? No, smallest class would be the least amount of members, which would be the naturals. You see what I mean?
Yeah, that makes sense.
Yeah, sure. I would say the main one that it belongs to would be the smallest class of numbers.
I'm gonna go with one, but just like I was just like talking about it. So it's also gonna be
Mine would be
Q's irrational. What's rational? Sorry, I just completely lost.
Q is rational, and
Okay.
irrational we don't actually. Okay, yeah, we have a. We usually don't refer to the class of irrational numbers because it excludes like every other number, like integers and these sorts of things. So we don't have that nice kind of like inclusion inclusion line with the irrational numbers. Okay, let's come back together and talk about these as we go along. Okay, so what I kind of hastily appended to this activity was that we should search for the smallest class of numbers to which these belong. Now, what I mean by smallest is as follows. If I take the natural numbers, okay, this is what I call the smallest class of numbers, because if I think about it as like a bucket where I put in all of these different numbers, right, then if I want to expand my set to be like the integers, then I need a bigger bucket because I'm putting in way more numbers, right? And if I go to the rationals, I need a bigger bucket because not only do I have to fit all the integers in there, I also have to fit all of the fractions in there, right? So this is what I mean by larger sets or smaller sets of numbers. It's also could be referred to as a more general description as opposed to a more specific description, right? So when I say we should find the smallest class of numbers to which the number 1 belongs, then we can look for the smallest bucket which 1 belongs to, which I think is the what? The naturals, right? So I would probably write something like 1 is in the naturals. And you could go ahead and also write that 1 is in Q if you want. It is. Or 1's also a real number. But this is kind of like the most specific thing we can say about the number 1, which was kind of what I was going for here. But if you listed them all out, that's also cool too. All right, how about negative 1? What's the smallest class of numbers to which negative 1 belongs? Integers, right? Because it's not a natural and it's not a whole number. Okay, so what's the symbol for the integers look like? It's a Z with an extra line. Okay, how about, let's do one more. Pi. And this one's a little bit confusing because as I was discussing with Gavin, okay, I kind of told you in between the rationals and the reals, I told you about the irrational numbers. And a common misconception is that, well, we have this nice like inclusion ladder, and then you'd say, well, if I take the rationals and I just like also throw in all the irrationals, then I'll get the irrational numbers. But actually, the combination of all the rationals and irrationals gives us the real numbers, okay? So if you talk about just a bucket with only irrational numbers in it, we usually don't refer to that set very often. But if you're curious, it actually is the same size as the real numbers. So that's just how small the number of rationals are. Okay, so in this case, for the smallest set of numbers, which I'm aware of, which is on this list, which includes pi, would be the reals. Okay, so in that case, I would say pi is a real number. Okay? All right, any questions on that exercise? Does that feel fairly okay? All right, classifying different types of numbers. All right, we're going to move on and talk about something else, which is the real number line. And we're also going to talk about intervals, okay, which is another type of set of numbers. Okay, so what do I refer to when I mean the number line? Yeah, that's right. I'm talking about the thing you learned in first grade, where we talk about how we have all of the numbers and we line them up. We're like, okay, who's tallest? You go here, you go here, you go here, you go here. We're lining them all up. So the one that's going to be perfectly in the middle is, of course, 0, right? And we call this point or location on the number line, because right now we can talk about location, right? Because we're comparing these numbers, we're lining them all up in order of their value, right? So now I can talk about a location because I'm on a line, which is like a space, where I can be at some point in space, or I could be at another point in space. So the very middle point of that space is what we call the origin. Okay? So the origin refers to the location on the real number line where 0 is located. That's the origin. Or if you're in the Cartesian plane, then the origin is 0, 0, right? It's where the x and y axes cross. Okay, so let's talk about inequalities. So, okay. So if I write x is larger than 6, then we can infer that x is a number larger than 6. Okay, so when I write a symbol like this, it means larger than. Okay? So the way it was taught to me when I was a youngster was that this is like the mouth of an alligator, and the mouth of the alligator wants to eat the biggest possible number, right? So the mouth of the alligator wants to eat the biggest possible number, so it faces towards whatever is the bigger prey because it wants to have more food, because it's a hungry alligator, I guess. Okay, so if we do x is less than 6, then this refers to x is going to be a number which is less than 6. Okay, and then the only difference with the line underneath is that we're also going to say x is a number which is larger than or equal to 6. So what's the difference between x is larger than or equal to 6 and x is larger than 6? It could be 6, right? X cannot be 6 if x is larger than 6, because 6 is not larger than 6. 6 is equal to 6. Does that make sense? Okay. I know, this is probably very boring for some of you, but we just got to go over it because it's in the review. Okay, so what does that look like on the number line? Okay, well, we can actually graph this. Let's graph x is larger than 6 on the number line. Well, what I'm going to do is I'm going to draw my number line, and if you want to, you can put the origin on there. It's sometimes helpful to have the origin. And I'm also going to put 6 on there. So where is 6 relative to the origin? To the right or to the left? It's to the right, okay, because it's bigger. It gets bigger as we go to the right. So here's 6. And if I want to graph this, here's what I would do. I know that x could be any number which is bigger than 6. So what I'm going to do is I'm actually going to fill in with a squiggle or something all the numbers which are bigger than 6. Okay, this is how we graph this inequality. Okay, and what about at 6? What am I going to put at 6?
An open circle?
An open circle. Very good. When am I going to put a closed circle? When it's equal to. Okay, so let's do x is less than or equal to 6. Let's see what that one would look like. If we did that one, then we would get, here's 6, and I would put a closed dot. By closed, I mean I'm going to fill it in with my pen. And then I would draw a line like so. Okay, so that's how we graph inequalities on the real number line. Okay, I got some time left. Let's finish up intervals here. Okay, so an interval is a set of numbers. You're going to notice that pretty much everything we're talking about today is sets of numbers, right? So we have the numbers which are real, we have the numbers which are natural, we have the numbers which are rational, and that sort of thing. And now I'm going to form a new bucket. And in an interval, okay, I'm going to include every single real number which is larger than one number and smaller than another number. So the way we draw that, or the way we write it algebraically is as follows. We draw a closed interval as something like a comma b, where a and b are real numbers. So I'm going to do a comma b in R. Okay, or for open intervals, we'll do a comma b with parentheses. Okay, now what we refer to when we talk about this is, for the closed interval, it is the set which contains every real number which is larger than or equal to a, so let's call it x, which is larger than or equal to a, and x is less than or equal to b. Okay, so let's have an example. 2 comma 3. If I do this set, 2 comma 3, then I'm talking about all of the real numbers which are bigger than or equal to 2 and smaller than or equal to 3. So how about 4.5? Inside or not inside this bucket? Not inside, because it's not smaller than or equal to 3. But how about something like 2.5? Yes, is a member of this set. Right? This is the new set. Okay. How about 3? Is 3 in this interval? It is in this interval, right? Because in this case, b is 3. So we want all of the real numbers which are less than or equal to 3. So if I draw a bracket like this, then 3 actually will be inside of this bucket. That's the big difference about open intervals. If I do an open interval, then I'm not going to include the endpoints in this set of numbers. Okay, so this one is going to be the same as this. Yeah, I'm cheating. Sorry, you can't do this on your actual notes. We're going to do x is larger than a and less than b. Okay? Every real number x which is larger than a and x is less than b. Okay, so what does this look like on our number line? Let's draw it real quick. So let's just do 2, 3. So we got 2 here and we got 3 here. So what the closed interval looks like is it's going to be all of these numbers on the real number line which are in between 2 and 3. And what am I going to do at 2 and at 3? Closed circle. Okay, so the closed circle goes with the square bracket. Okay? Closed circle goes with the square bracket, and it also goes with the word closed, right? Okay, and then we could do something like the other one. If I did 2 comma 3 with parentheses, then I would put a 2 here, and I'd put a 3 here, and I would fill in, again, every single number which is in between, except at 2 and at 3, I'm going to do an open circle this time, because that's to let us see visually that 2 and 3 are actually not in this set. Okay, so we have a couple different sets of numbers. We can say I'm putting inside my bucket every number which is of this form, or I could say I'm going to put in my bucket every number which is larger than this one and smaller than this one, or something like that. Or I could just do every number which is larger than 4, right? That would include all the numbers from 4 up to infinity, right? Okay, so let's just take a quick look at a table here. This is to help us visualize. Some different types of intervals that we could see. So we've got our open interval up at the top. Okay, so another thing that you sometimes see other than closed dots or open dots is you'll see like they'll actually put a bracket or a parenthesis. If you prefer to do it like that, that's fine. That's how our book does it, apparently. So, okay, what else? Do we have anything else interesting here? Okay, one interesting thing I want to talk about is this weird line. What is that weird line about? Okay, so this is kind of like saying the following. The way we read this mathematical notation is x is a number such that. So this line here means such that. So here we put x, this is the type of thing that we're describing. And then here we're going to put the rule which that thing must obey. So we say x is a number such that x is smaller than or equal to b. Okay, this is how we read this notation. And the interval notation is like so, and the graph of it on the real number line would look like this thing here. Okay, so one more thing that I want to talk about is we can also have sets which are described by not by a positive description of the number, but by like a negative description of the number. So what do I mean by that is if I say x is a number such that x is not 1, okay, then this is a set which refers to all of the numbers which are not 1. i.e., if I were to graph it, what would it look like if I were to graph all of the numbers which aren't 1 on my number line? Yeah? Yeah, I'm going to put an open circle on 1, and then I'm going to fill in everything else. Okay? That's how I could do something like that. Okay, and that's going to be important because later when we talk about rational functions, there's going to be numbers which cannot be in the domain of that function, and we're going to use this notation to talk about those. Okay, we'll close there for today. See you all tomorrow, and we'll talk more.